Hi everybody, my name is Serena Danese. I'm from Switzerland, from the University of Zurich of Applied Science. And I want to show you what we did for this project as demonstrator. So we, with our demonstrator, we want to control the humidity and the temperature in a greenhouse. What especially is a commercial greenhouse. You can see here the picture. So we have a quite large room of this greenhouse, and this is the reason that we had to install 9 absorbers. So the absorber in the picture are these gray box. So we have on all the parts, and so we control humidity and temperature. In addition to that, we develop a new system to inject the air in the greenhouse that I'll show you later. And with this system, it is able to save more energy. We ran some tests during the winter, last winter, and during the summer, and we saw, especially for the winter, that we can save a lot of energy. I try to go to the next slide, but okay, here. So this is a picture of one absorber. It was the first absorber that we installed in the greenhouse, and now it's in our lab at the university. You see it's transparent, and the reason is so we can control what happens inside, if there is some dirty, if the distribution of cell solution is good, and so on. On the right, you have a diagram of the system. Actually, it's the system that we have in the lab, but the construction of the absorber is the same. So in the lab, we take the ambient air, and then we have here in this box, we have the possibility to cool or to heat and humidify the air in order to create the condition that we want to test. The air, so then go in this way, so go from the top to the bottom. This is only a problem of the construction in the greenhouse, but the absorption process take place in this colored part. That means the absorption take place in this absorber where the air go from the bottom to the top, and in yellow you can see is the salt solution that go from the top to the bottom. The sand solution then is collected here in a sump and then is pumped around the absorber in this way. How we can control the temperature and the humidity of the air? So we control the temperature of the air through the temperature of the salt solution. We have here an heat exchanger, so we can heat or cool the salt solution depending on the temperature that we want to reach in the air. Oh, sorry. The humidity of the air is controlled through the concentration of the salt solution. So we did manually in the lab, but we can change the concentration of the salt solution in order to reach the required humidity. Of course, so I take the example of absorption. During the absorption, heat is released because the humidity is absorbed, so we have condensation process. And we control the temperature of the air through the heating the salt solution. But we need less heat than without the absorption process, because we use also the latent heat that is released during the absorption to heat the air. And this is the tricks of to save the energy of this technology. If I go to the next slide, so I told you before that we develop a new system to inject the air to the crops in this greenhouse. You can see here a small schema. So we inject the air directly to the crop. So here on this picture is below the table. You see we have this pipe. This pipe has small holes, and through these holes we inject the air. That means we control the temperature not of the entire greenhouse, but we control the temperature only above the crops. In this case, we have two advantages. The first is we don't need, if you see, we don't need to temperate the entire air of the greenhouse, that is, the volume is huge, but we control just the temperature here. That means we need less energy. What is interesting for the greenhouse, for the crops, for the plant, is the temperature around the plant. And the second advantage, you see this is a huge greenhouse. In our demonstrator, it's not the case. We have only flower, the same kind of flower, but actually you can have a type of plant here, a type of here, and another type of here. So different type of plants, crops, which maybe require different temperature and humidity. And with this system, so we control the temperature and humidity of each single table. That means we can also create different climate inside the greenhouses. Here I want to show you the results that we did. So we did some tests during the winter and during the summer. Here I show you the test that we had last December 2018. So on the left, we have the relative humidity, and on the right, the temperature. What is interesting, if we have a look to the diagram with the humidity, you see this line is the humidity of the greenhouse. This other line in pink is the humidity at the inlet of our absorber. So you can see that it's already quite different. And the horizontal line are the humidity at the outlet of each absorber. What is very interesting, so you can see that we can maintain the humidity quite constant. So the variation is very small. And also with this system of injecting the air below the table and control the humidity only above the table, you see also which is the huge difference between the humidity that you control if you have a common system in a greenhouse, so you control the air in the greenhouse, and the humidity that we have around the table. So the difference is huge. That means we have to control this one and on of the greenhouse. The same happened with the temperature. So in this day, it was in December, it was quite cold. We have the temperature outside of the greenhouse was more or less 0 degrees. And you see here again, the temperature here in that dotted line is the temperature of the greenhouse, and above is the temperature of the outlet of our solver. That means if you work control with the standard system, the temperature of the greenhouse, you have to have 25 degrees, you have to increase this temperature more, and that means at the end you have too high temperature around your crops. But what is interesting is to see the energy that we required. Left is the energy that we require in the greenhouse with the traditional system, and on the right with our traditional system. The traditional system in the greenhouse consists of two different systems with hot water, one below the table and another one above the table. Now we have a look to the light blue and yellow line. Here is the scala. So they are the energy required of the system below the table in blue and above the table in yellow. The experiment was did between 10 o'clock and 4 o'clock. And we see in this day, where we didn't have absorber in operation, we need more or less 300 kilowatt hour to maintain a constant temperature. The same we did on the right, where we had the absorber in operation, or the absorber in operation. In any case, we maintain the heating system also in operation to guarantee the 25 degrees. But what's very interesting, so with the absorber in operation, we need only 50 kilowatt hour. So it was not the same day because it was not possible to do it in the same day, but the outside temperature in both cases was around 0 and 5 degrees. So you see that we save quite 70% of the energy to heat the greenhouse. We did also some tests during the summer. Unfortunately, here it's not possible to compare the energy required with our system and with traditional system because there is not a traditional system at the moment. So they don't have the possibility to cool during the summer. What we see here on the left, between 12 o'clock and 8 o'clock, our absorber was in operation. So in blue is the temperature of the greenhouse, and here in red is the temperature at the absorber outlet. So we were able to decrease the temperature more than 10 degrees. On the right, okay, this diagram is not so easy to read, but there are the humidity. I don't have all. So this is the humidity at the inlet of the absorber, and in pink is the humidity at the outlet of the absorber. Unfortunately, this is the absolute humidity, not the relative humidity. Sorry, it's the relative humidity, not absolute humidity. And so we cannot see, but it was an absorption process. So we remove also in summer a lot of humidity from the greenhouses. This is what happened in summer. You have also here a picture of our table. So the number one is the air at the outlet of the absorber. So we are here. You can read the temperature. We have more or less 20 degrees, and the humidity. This is a more the humidity air diagram. So before to reach the crops, the air was eaten up from the heat of the greenhouse. But then the crops, so on the table, there was some water. So we have a evaporating cooling effect. So from 1 to 2, so the air is heating up. Then we have a cooling down. This effect is the evaporation cooling that is possible only if the air is dried. We did this in our sorb. Then we have from 3 to 4, the transpiration of the plant. And for 4 to 5 it was above in the more or less 2 meters above the plant. So we have also another heating effect. But what we can see that is 5 to 1 is what happened in our absorber. So this 5 to 1 is the effect of our absorber. Then the other depend of the configuration of the greenhouse, of the table, the kind of crop that we have. So the potential of our absorber is quite huge. We see that we go from more or less 40 degrees to 20 degrees. And also we reduce the humidity from 0.014 kilogram per kilogram water per kilogram air to 0.007. So these are a short presentation about what we did in a greenhouse, and I can show you a short video so you can see what we really installed there. So Marco, you can show the video if we have time. So I repeat, the demonstrator was installed in this greenhouse. You see it's a huge greenhouse, and from of this greenhouse we have the part here that is a room with 600 square meters. So we install our demonstrator only in one part of these greenhouses. Here is this room. So you see the table. The table are also particular. We have this special white wall to avoid that cool air fall down before to reach the plant. This is the absorber. So we take the air from these orange ducts. So this is the absorber. The fan is integrated to the construction of absorber. This is the part, it's difficult to see, but this is the pipe of salt solution. So this orange is the valve for the salt solution. And here is the sump where it's integrated the pump for the salt solution. So solution actually see like water. So we have two different sectors in the sump to divide the concentrated salt solution to the diluted salt solution. And this is the special absorber that we install also in the greenhouse. It's design of Watergy. It's a different design, and we want to compare the two different designs. So of course we have a system, a national instrument system, to measure all the temperature and the humidity. You see, we measure the humidity direct above the table in order to control the temperature required from the plant. And these are the pipe below the table with this hole. So the air is injected direct on this grid. And this is the absorber in our lab at the university. So we have this transparent absorber. We can monitor everything. And this wood box is to control the air and humidity of the air, the inlet of the absorber. This black is the distribution of the salt solution inside the absorber. We have this fill package in order to distribute really very good the salt solution and to increase the contact surface between the salt solution and the air. And like in the greenhouse, also in the lab, we monitor all the value of temperature, humidity of the air, flow rate of the air, and then flow rate of the salt solution, temperature of the salt solution, the computer. And also we can calculate directly which is the energy go from the salt solution to the air. Okay, this is the video.
So the opportunity that we've been exploring is really around kind of an industrial opportunity for looking at installing HDisnet technology. We've been working with data from the local automotive manufacturing plant here in Newcastle, which is a very large scale manufacturing of on-road vehicles. And they've kindly provided us with technical data in terms of the way energy is utilized across their site. And in those discussions, we have been able to articulate a good opportunity for the installation of the technology. So in automotive manufacturing, you can see here from this slide here, there are a number of different elements to the manufacturing process. And when you break those down in terms of the way that the energy is utilized, the majority of energy that's utilized in automotive manufacturing process is from the painting system itself. So as you can see from the breakdown on the table there, that can be between 27 and 50% of the overall utilization of energy on such a site. And that's also kind of fits within the context of things like heating, ventilation, and air conditioning. What we're going to use as well as compressed air systems as well. So within this framework, there's a lot of excess heat on site, and we wanted to try and use that to facilitate and offset some of the air conditioning costs that are going on site. So the paint shop was where we focused our activity. The paint shop produces a lot of heat, and you can see from that first image there on the left-hand side, there is different ovens that you go through in painting of a vehicle that heat up the surface and cool it down quickly to make sure that the material sets in a nice, efficient way. So you've got, in parallel, lots of heating and then sudden cooling going on. Also within the process, you can see with that big red circle there, there's a process which basically at the end of the painting process, all of the air with all of the volatile chemicals that exist in it, that needs to get burnt in what's called an RTO process, which you use to burn natural gas. And you basically burn all the air as it comes out to burn off these volatile organic chemicals, because these are an environmental challenge. So when you start to break down where does the energy come from across that process, yes, it's coming from the ovens and it's coming from the painting booths. The idea really is to try and get that paint booth to be at the right humidity and temperature to ensure that when the paint sets or dries, it's actually the kind of quality that you want to see on the side of a posh new car. If you get the humidity wrong, you get that kind of image there at the top called checking. And if it's too high, the humidity, you end up with blistering on the surface. So just to give you an impression, an idea there of what it looks like if you get it wrong. So at the particular site that we were interested in looking at, we found that the kind of standard air handling units are unable to deliver the narrow range of temperature and humidity that you might want. So they need to do lots of things like air conditioning and heating in order to maintain a 23 degrees centigrade and a relative humidity of 70 degrees. And you can see that actually the tolerances of those have got to be within 1% and 1 degree. So the challenge is that across different times of the day, you know, particularly where we are, it's obviously lower than 23 degrees most of the time. So we need to find ways of handling that. And of course, this is obviously exacerbated by the fact that these processes are almost working 24 hours a day. So you've got nighttime temperatures and nighttime humidities also to consider. So the HDISNet installation, the idea is that we take all of the temperatures that we see across the day here in our analysis, and we need to upgrade those in order to hit the optimal condition for the paint booth. And we would use the liquid desiccant technology in order to achieve that and provide warmer and more humid air. We would use the source of heat from the heat recovery process from the other parts of the paint shop to power that system. And in summary, we found that across different times of the day, we had different heating and cooling demands, but overall, the technical viability of the system is viable. To achieve this 23 degrees and 70 humidity, we costed up the system and worked up how much this kind of retrofit solution would cost. And we determined the the return on investment costs for the technology. And we found that that's slightly under 3 years for when you work it all out in all of the detail that you need to for these kinds of analysis. And this savings are really realized through using lower amounts of gas and lower amounts of electricity on site. And then I guess that's my last slide. So we've got a few minutes for questions.
Yeah,
I guess
thank you, Andrew. Thank you very much. Yeah, we have 5 minutes for questions. If you have questions, please raise hand or just unmute and start. Any questions?
Hello, is this working?
Yeah, we can hear you.
Yes, great. So it's a question just to make sure that I understand properly. So if we think about these cases now in the context of a network, to me it looks like, for example, the greenhouse would be at some point in time a consumer of heat, and at some other point in time, for example, in summer, it would be a provider of heat. So am I picturing this correctly, or?
Yes, you are correct. So also the absorber configuration is valid for the both case. Depending which situation we have, the equilibrium between salt solution and air, we can heat or cool down. What we see in this summer, we needed in any case to remove the humidity from the air. That means in the absorber, we wanted to have an absorption process. That means the absorption process release also heat, and we had to cool down the temperature of the salt solution. But in any case, then we have this evaporating cooling on the table. That means at the end, the total energy that we need is always lower than with the traditional system.
Okay.
In the case you need to increase the humidity of the air, you can also use this box, the absorber, this column, to increase the humidity and cool down.
Okay,